Chapter 6. Oxygen Precautions and Preparing Nitrox. Using oxygen at a high partial pressure can be very hazardous, so learning how to use it safely is an essential element of diving with nitrox. In this chapter you will learn about oxygen precautions, the fire triangle, the 40% rule, and the methods of making nitrox. By the end of the lesson, you will be able to state the precautions that must be taken when around oxygen, describe what the fire triangle is and how it applies to nitrox use, describe oxygen cleaning and what scuba equipment must be cleaned for nitrox use, define the 40% rule, describe how cylinders and valves are prepared for nitrox use and how they are marked as nitrox cylinders, and list the 5 methods that are used to make nitrox and which are most common. In the Earth's atmosphere, with its oxygen fraction of 0.21 atmospheres, and at normal temperatures, materials do not spontaneously ignite and burn. A source of ignition, heat, is required to initiate burning. After a material, fuel, is ignited, then the fire itself provides the heat to sustain burning. Firefighters use the concept of the fire triangle. In order for a fire to occur or continue, 3 things must be present: fuel, oxygen, and heat. If any one of these is absent, a fire will not start. If any of the 3 is removed, the fire will be extinguished. When a fire has consumed all available fuel, burning ceases. If the fire is sufficiently cooled, as by dousing it with water, it will go out. If a carbon dioxide fire extinguisher is used to remove the oxygen around the fire goes out. But, as the fraction and partial pressure of oxygen increase, many materials that do not burn under normal conditions will burn if ignited. Also, any fuels will ignite more easily. Materials that are of little concern in air may become quite flammable in an oxygen-rich environment, and even more so in a high-pressure oxygen-rich environment. Petroleum-based products and other hydrocarbons are of special concern because they ignite extremely easily in a pure oxygen environment. Other materials, though they may not become flammable, will oxidize and degrade much more rapidly in the presence of hyperbaric oxygen. When high pressures of oxygen are going to be present, extra care must be taken to prevent the fire triangle from occurring. Equipment that will be used with pure or very high concentrations of oxygen must be specially prepared to withstand the oxygen and to prevent fires and oxidation. The way that nitrox is prepared will be discussed later, but the most common mixing method involves introduction of pure oxygen at pressure. All equipment systems that will be so exposed must be specially prepared in order to withstand the oxygen. Hydrocarbons and petroleum-based products must be avoided. This includes not only petroleum-based compressor lubricants, but also the silicone lubricants normally used in scuba air systems. Neoprene, silicone rubber, plastic and metal shavings, even finely divided particulate matter all become potential fuels for a fire in an oxygen-rich environment, especially one at high pressure. All equipment to be used with pure oxygen must be cleaned for oxygen service. The equipment itself must be oxygen clean, and oxygen-compatible parts must be used in order to minimize the risk of fire or destruction by the oxygen. Oxygen clean means that any potentially flammable contaminants have been removed. Oxygen-compatible means that the materials used in the various parts in the system are not flammable or readily oxidizable in the presence of high pressure or pure oxygen. This special oxygen cleaning can be complex, involving an initial cleaning using solvents that removes all hydrocarbons, and then the use of special oxygen-compatible lubricants, O-rings, seats, seals, flexible tubing, etc., as the system is reassembled. Even though certain materials may not be flammable in the presence of high-pressure oxygen, more durable materials that do not so rapidly degrade will be substituted. Formal oxygen cleaning, which is required in many industrial and governmental applications, such as NASA, requires adherence to very strict procedures as well as careful documentation. After cleaning, future contamination must be carefully avoided, or the whole oxygen cleaning process will have to be repeated. Even skin oil from a finger can contaminate formerly oxygen-cleaned equipment and necessitate re-cleaning. Care must also be taken to avoid sources of ignition, the third side of the fire triangle. A sudden increase in system pressure could elevate the temperature in the system sufficiently to cause ignition of any contaminants. Valves should be opened slowly to prevent a sudden increase in pressure with an accompanying rapid temperature rise. Even a static spark from a rug or opening a Velcro closure could cause ignition in a pure oxygen environment. When is oxygen cleaning necessary? As a recreational nitrox diver, you will dive with an ordinary, well-maintained regulator. But your cylinder will have been cleaned for designated service as a nitrox cylinder, and it will be clearly marked as an enriched air nitrox cylinder. The general rule of thumb is that any equipment that is to be used with pure oxygen or an oxygen level that is above 40% and at a pressure above 200 psi must be cleaned for oxygen service and have only oxygen-compatible parts. This so-called 40% rule has gained acceptance over time, although there are no published test results to show that 40% is the absolute limit above which oxygen cleaning is unequivocally necessary. No definitive industry-wide standards exist for handling gas mixes intermediate between air and 100% oxygen. The U.S. Navy handles gas mixes up to 40% oxygen the same as air. The Occupational Safety and Health Administration has set a 40% breakpoint, above which special cleaning is required. NAUI and the recreational diving industry as a whole have accepted the 40% rule, and Nitrox 40 is the accepted upper limit fraction of oxygen in recreational nitrox diving. 40% seems to be a valid limit in the sense that at or below this level, oxygen compatibility problems have not occurred. Above 40%, one is in the gray area for which there is seemingly no firm data. Flash combustion has occurred above 40% oxygen, so it is better to err on the side of safety. Technical divers use higher oxygen fractions, such as in a decompression gas mix, use scuba equipment that is specially serviced, and is fully oxygen clean and oxygen compatible for these special applications. So what about your own regulator and your cylinder? Your regulator will not encounter an oxygen level above 40%, so the rule applies. Normal maintenance service is sufficient for your regulator. Of course, as with all of your equipment, you should take care of your regulator, rinsing it after dives, keeping it clean, avoiding extreme heat, and having it serviced regularly. The same general cautionary statement is true of all scuba equipment that will be used with nitrox up to nitrox 40, submersible pressure gauges, BC inflators, BCs, etc. For all scuba gear, cleaner is better, and the prudent diver takes good care of his or her life support equipment. Your cylinder is a different matter. The most common way to prepare nitrox is to introduce an initial quantity of pure oxygen into an empty cylinder, which is then topped off to service pressure with specially cleaned air. Every time your nitrox cylinder is filled, it is subjected to pure oxygen at high pressure. So, your cylinder must be dedicated to nitrox use. This means that it will be cleaned before it is used as a nitrox cylinder. After being cleaned for use with oxygen-enriched air, the cylinder will be labeled to clearly identify it as a nitrox cylinder. The label has a green band 4 inches wide that is bordered above and below with a narrow yellow band. An identifier such as nitrox or enriched air nitrox is printed in yellow on the green band. Partial pressure mixing systems are the easiest to set up, requiring only a source of high-pressure oxygen and a source of clean high-pressure air. The air used for nitrox blending must meet the higher standard of purity with a lower hydrocarbon level than ordinary scuba air. In partial pressure mixing, the blending technician first puts a measured amount, pressure, of oxygen into the cylinder, and then fills the cylinder to its service pressure with air. For simplicity, blending a nitrox fill normally begins with the cylinder emptied of any previous mix, but it could start with adding oxygen and then air to whatever remained in the cylinder from the previous use. Continuous flow mixing was the method that was first used by Noah. The continuous flow method injects a measured flow of pure oxygen into the air before it reaches the intake of the compressor. The oxygen-air mixture is then compressed. As the high-pressure nitrox exits the compressor, the oxygen fraction is analyzed online, and the oxygen flow at the low-pressure intake is fine-tuned, either manually or by automatic feedback control, until the desired blend is attained. The high-pressure nitrox is routed to a bank of storage cylinders, from which it will be drawn to fill individual scuba cylinders. Pressure swing absorption is a method that removes nitrogen from air rather than adding oxygen to it. Pressure swing absorption, or PSA, uses a material called a molecular sieve that selectively adsorbs a thin layer of nitrogen onto its surface from the air that passes over or through it. Technically, the process should be called pressure swing adsorption with a D, because nitrogen only adheres to the surface of the sieve material and is not sucked up by it. The adhering nitrogen can be easily removed, so the material can be reused repeatedly. The amount of nitrogen that will be extracted from the air is largely a function of the pressure of the air as it is delivered to the system. This pressure is only about 3 to 6 atmospheres. Two beds of the nitrogen-adsorbing molecular sieve operate in parallel. The incoming filtered air passes over each in turn, alternately. As one bed is removing atmospheric nitrogen, the other is depressurizing and releasing the nitrogen that is adsorbed on the previous swing. Oxygen up to 95% purity can be made using this system. The balance is argon, which is about 1% of the incoming air and is not adsorbed by the molecular sieve. The gas emerges at low pressure, and if nitrox rather than oxygen is the end product, it must be compressed to fill scuba cylinders. Usually, a PSA system feeds directly into a continuous flow system to make oxygen-enriched air. Membrane separation is also a nitrogen removal process. Instead of a molecular sieve that adsorbs nitrogen, membrane separation uses a semi-permeable membrane that allows oxygen to flow through it more readily than nitrogen. Filtered clean air is introduced under moderate pressure, 12 to 18 atmospheres, and flows through the membrane. A valve on the output side controls the flow rate of gas across the membrane. The higher the flow rate, the higher the oxygen fraction of the product gas. The oxygen content can be precisely controlled, and preset controls from the manufacturer limit the maximum to 40% oxygen. The product nitrox is then compressed for use in scuba cylinders. As a nitrox diver, you are responsible not only for your dive planning and execution, but also for your equipment. You should keep your gear well maintained, be careful in its use, and keep it clean. Your cylinder will be a dedicated nitrox cylinder, and although sometimes it may be filled with air, nitrox 21 as some call it, you should obtain your air only from a fill station with a compressor that supplies nitrox-compatible grade air. Another air source could possibly deliver air that would contaminate your cylinder for future partial pressure blending. Your responsibility for your breathing gas does not end with keeping your equipment clean and obtaining your oxygen-enriched air from someone whom you trust. A unique feature of nitrox diving is that the end user is responsible for the correctness of what he or she will breathe. You are responsible for your cylinder's contents being what you asked for. A final step before you take the cylinder away with you is verifying the contents. The next chapter will discuss this last step, analyzing your gas and correctly labeling your cylinder. Planning and conducting safe nitrox dives must include safety precautions required for higher partial pressure of oxygen and keeping equipment clean. This chapter covered oxygen precautions, the fire triangle, 40% rule, and methods of making nitrox. Now that you are familiar with oxygen precautions and preparing nitrox, you should be able to state the precautions that must be taken when around oxygen, describe what the fire triangle is and how it applies to nitrox use, describe what oxygen cleaning is and what scuba equipment must be oxygen cleaned for nitrox use, define the 40% rule, describe how cylinders and valves are prepared for nitrox use and how they are marked as nitrox cylinders, and list the 5 methods that are used to make nitrox and which are most common.